I think others may join later. Now, today we are going to discuss the few things related to the another protocol, which is known as synchrophasor based protocol. So it is a protocol known as IEEE C37.118. So it is the protocol which is used for communication among synchrophasor devices. So whenever you have any synchrophasor devices like PMU, phasor measurement unit, and PDC, phasor data concentrator, so then how the PMU will communicate with other PDC. So that related to that and how you can or we can do the attack on this data which is or packets which is transferred by the PMU to the PDC. Higher, it is of course hierarchical level. So one has to know the hierarchy of the PMU devices. So we will discuss this thing in today's session. Uh, and later on, we will also discuss the just the comparison of the three protocols which are important. Uh, Professor Sidhu has already given the highlights of the IEC 61850. So we will see how IEC 61850, what are the main characteristics. He has covered, so I am not going to cover it. Then we have the another protocol, which is DNP3 protocol, which is widely used for SCADA systems. And we do have the third one protocol, which is IEEE C37.118, which is used for synchrophasor devices. So we know that the government has the planning or government has already planned. They have already installed several PMUs, right, in our country under the scheme. I think URTDCM, that scheme government has run. And based on that, now the till now, if we consider we the whatever PMUs we have installed, I think more than 1500 PMUs we have installed in our country. But these PMUs are not using for any, let's say, what we can say, any detection part or any other part. It is just simply remain ideal that okay, you can have the PMU and they are taking the data. That's all. These PMUs are not used for any decision making, right? Still, in our country, all the decisions that is to be taken based on SCADA based systems only, right? However, obviously, maybe within as the time progresses, in upcoming 3-4 years, the decision making that will be done based on PMUs also, right? Because that is obvious. Because if you have PMUs, we know that it's a, data rate and all other benefits are there compared to the SCADA system. So this also we will just see the in one slide what are the important differences between this among these three protocols: DNP3, 61850, and the this one synchrophasor protocols, that is IEEE C37.118. Right. So that also we will discuss. And after that, depending upon the time, we will also discuss what are the different types of attacks that can be done on this synchrophasor stream of packets. So when any PMU sends data to PDC, then what are the different types of attack can be done, right? And what are the impacts of that? How we can, let's say, avoid or how we can mitigate those things. So that also we will discuss, right? And whenever the mitigation part comes, right, of course, for 61850, maybe client server communication, or for others, as Professor Sidhu indicated, that we can use the cryptography, right? That means we can use either public private key or maybe digital certificates or any other. But again, the major issue with all those cryptography is that it is going to add time delay, right? And nobody is going to talk about time delay, right? Why? See, you know that cryptography has been invented for long time, right? 2 decades ago or 3 decades ago. But still, uh, uh, I did not find any papers, or I did not even see the manufacturer who has used cryptography in our power system applications, especially time critical applications, right? Where you have to use only the one or two layers. You have to bypass the other layers to have the faster responses, to get the faster responses. So there, the only whenever you have cryptography, obviously you have a time delay. It is similar to we have studied at undergrads. We are using filters, right? Maybe active filter, passive filters. We are using to remove the unwanted noises or harmonics and so on. But again, whenever you add filters, there is a time delay, right? Delay is there, of course. There are other issues are also there. Whenever you add delay, whatever phasor data you are calculated, the angles of phasor data that is changed, and so many other things are there, right? But major issue with filters are they are going to add time delay. And whenever whatever filter you have, uh, let's say you take very fast filters, right? Then also there is an addition of the delay of, let's say, around half cycle delay, right? Maybe 8 to 10 millisecond delay. Now when you are taking decisions in one cycle, let's say differential relay, right? For transformer or some other applications, DC microgrid, where you need a very fast response in 4 milliseconds, 6 milliseconds, compared to our AC system, where you can have the time, let's say, up to fault clearing time may go up to 3 cycle, 4 cycles, like that, right? One cycle relay time, and again 2.5 to 3.5 cycle your breaker time. So this is there, but as soon as you add filters, there is a time delay. So there is a paper, right? How much time delay that is to be added when you use filters. So same way, the papers that is there are also there related to cryptography. That whenever you add cryptography, how much time delay is there, right? And whether you are able to, let's say, correlate this time delay with your time critical applications or not. So that is the major aspect, right? So if you just consider the cyber, okay, I will change from here. I think it is not working now. Okay, so if you just look at, just hurriedly, I will take not more than 5-10 minutes because this is already covered, right? Not this way, but some other way. So when you define any cyber physical system, it has two things. One is a physical system and another is your cyber system, right? And in physical system, you have the, let's say, some physical process is going on. We will see the example also. And then based in this physical process, you install some sensors, right? Maybe what type of sensors you install, it depends, right? Either infrared, IR, or any other sensors. So then they are going to take, or they are going to acquire the data. They take some, let's say, data acquired, and then they give it to your cyber physical system, right? Where the communication network is there, either wired or Wi-Fi. And then some algorithm is going to run here in your control center. Depending upon the output of the control, this algorithm which is there in the control center, it will again pass this to the actuators. Actuators are the, let's say, some corrections required. It is a basically a closed loop system type of structure, right? Where you take the, let's say, error, and whatever error in the form of corrections are required, that again you pass on to the physical process, right? So this is more or less structure is there. Now the best example is our DC motor, right? Let's say my physical process is nothing but my DC motor, and I have some sensors installed, so I am taking data of DC motors. You can take voltage, current, speed, whatever it is, right? So let's say I am taking data of speed. Now this data that is passed on to my some algorithm which I have written through some network, right? Maybe wired or wireless, and whatever corrections are there, right? As per whatever algorithm you have written here, again you can pass on to the actuators. These actuators are nothing but it is going to control your motor drive, right? Basically speed, right? How you can correct the speed of motor, and accordingly it is this is going to adjust your speed. So this is the best example of our cyber physical system or network, right? The second example you can also consider regarding the traffic control. So physical process here is the vehicles which are moving on the road, and the sensors are the whatever cameras they are going to capture the data, right, related to traffic density and other parameters, and they are going to acquire this data and they are going to pass it to the traffic management software, right, which usually run from backend side, and then again from whatever the output you obtain from here, you pass on to the actuators. So actuators are your lights, again same thing, whether I want to increase the, let's say, the stopping time from 1 minute to 2 minutes, so that I can control the traffic density and so on, right? So related to that, this is also the another example of cyber physical system. The third example, that is again the car manufacturing, automobile industry, that is widely used. That, let's say, my physical process is the assembly line, where I am several robots are there. They are going to, let's say, manufacture or fit, trying to fit the cars, various parts of the car, and then we have a sensors. Let's say we are going to, from sensors, they acquire the vision, force, temperature, radio frequency identification, and many things. And then they pass out to the, let's say, some algorithm, right, which runs from backend side. And this algorithm again going to give the signal based on that. And then here you have the, let's say, some guided vehicles are there, or they are going to have the, let's say, pass on the signal. Let's say this robotic arm has to move this much degree, or this much correction is required, and so on. So this is also the another example. Another example is our own body, right. Whenever we want to measure the, let's say, blood pressure, then we usually, let's say, put the cuff of the device, right, a device known as sphygmomanometer, which measures the blood pressure. Of course we do have digital, this is not sphygmomanometer, but still doctors uses that analog one, right, which is more reliable than this one, right. This is not reliable. So then again they measure the blood pressure, and then they pass it to the device through some, let's say, communication medium, and then in the digital, let's say, your wristwatch, or in, let's say, in your mobile, you can watch it and you can take the corrective actions, right? But not using this digital meters, digital one. Okay. The thing is that the now if we consider the example of our power system network, then we have some, let's say, some network is there, maybe IEEE 14 bus or 30 bus or higher one, and you have installed several synchrophaser devices, let's say PMU, at different locations, and then they acquire the data, and then they pass on this data through some communication network to the higher level, higher hierarchical level. This is usually PMU will pass on the data to PDC usually, right? But here I have written some controller, right, for lab setup point of view. And then based on that, they will give some action to the breaker which is installed. As Professor Sidhu indicated, there is a ready-made text for boost messaging. So you just write that code, and or maybe copy and paste it, and accordingly the command will be issued. So this is also the another example. Uh, Now this all this cyber physical network works on your OT side and IT side, right? There is a, but there is no clear cut demarcation. We cannot let's say differentiate or discriminate between OT side and IT side, because here on OT side you have the various devices, smart devices, like starting from merging unit, and let's say you have IEDs, you have PLCs, all devices are there. You have RTUs, smart meters are also there. And then there you have a control center, of course, for within each substation you have your own let's say measurement or monitoring part. Let's say human machine interface is there locally, and then you have your main control center where all this data of different substations are gathered, and then you have the data exchange will take place, and your IT side people will monitor those data. So that will be there, right? That is the system. So this we you know very well, right, how this is done. Now before we just look at the what is the IEEE C37.118 standard, right? Uh, we must know that what is the payload capacity, how much data that is generated by all smart devices, right? For example, we have PMUs, we have, let's say, the other devices like smart meters. So how much data on per day basis this type of devices are going to generate. So this data payloads that comes under the, again, another area that is known as big data analytics. Right? That also is a big challenge, where you installed any smart devices and you gather the data. Now what to do, how to handle those data, right? That is again a big challenge. So whatever data we do have, right, normally this data that is divided in two parts. The one type of data which are available from utility measurement infrastructure, right? Utility measurement infrastructure means whatever smart devices you put, let's say fault recorders or any other devices you put, whatever data are generated by those devices, those comes under the this measurement infrastructure. And the other category that is that does not fall under the this measurement infrastructure other than this. So if we just look at what are the data, let's say data fall under the first type of category of the measurement. So we have the first under the utility measurement infrastructure category, synchrophasor data. So whatever data that is generated by PMU, that comes under this, right? The second is the your, let's say, metering data, right, which is used for revenue generation and some other asset management and so many other things, right? So those data that also comes under this category. The third one, that is the data generated by transient recorder, mainly used for fault location purpose, right? So that the maintenance or engineer can send the person or lineman just go there and see what happens at this distances. Fairly accurate to be, I think, 300 meter or maybe 1 or 2 kilometers, right? I think utility people can tell better. But usual accuracy is, I think, 500 meter to 1 kilometer, right? That is what they have claimed. The other data, that is the data related to asset management, right? That those data are also there. Those are generated. And the fifth one, that is the nameplate data and the some maintenance data which are entered by the utility person offline. So those, so these five different types of data that comes under the category of utility measurement infrastructure, right? Which are very essential. Now, some of the data, right, which are not essential, which falls under the second category, right? Those data are weather data, right? Because the weather data is also required very much. Geographical information system data, GIS data, lightning detection network data. I don't know whether we are, let's say, considering utility in our countries, not considering this data. I don't know. Maybe I may be corrected. Landscape and vegetation data, these are also there, and electricity market data. So this five, again, these five categories of data, they do not fall under the utility measurement infrastructure, but still they are there and they are going to, let's say, generate huge amount of data, right? So if you just and now how to deal with this data? So obviously, with both the categories of data, we need a correlation of data in time and space, both. This is very important, right? How to store, once you store, how to handle those data. Let's say, for example, you are storing all this data, right? Now sometimes, maybe for post-mortem analysis, you need some category of data. Now how to find out, right? It is similar to, let's say, you are doing PhD and you are working in some area. When you type something in Google, you will find 300, 400 papers. Now, how to, let's say, segregate those things? So same way, this is also another big problem, right, for utility. So you have to correlate the data in time and space both, and then you have to then provide unified and generalized modeling. So there are certain methods in this also, like data mining and so on. So you have to use those methods. Now, the problem with this data, all this what we discussed, two categories of data, they have the problems like three V's. Right? V for victory. So the first V, that comes under the large volume of data, right? The data generated, right? What quantity of data they are collected, right, by the PMU or some other devices. So they generate in terms of gigabytes, sometimes terabyte also, that is there. The second we comes under the velocity, right? Velocity means the at what rate those data are captured, samples per second value, right? So this is also very important. The first one, that is the volume of data, how much data you are gathering, and second, the rate at which those data are collected. Because if you have meters, then the rate at which data are collected by meters, smart meters, and if you have PMU, then the rate at which data are collected, both are different. Both are not same, right? So this is also another thing. And third, variety, right? Let's say I am acquiring weather data, right? Then those data comes or some other data, GIS or some other data, then those data comes from, let's say, seismic data I am acquiring, right? Though we are not acquiring in our country, but some other countries they are doing. So then you this the format of the first category of data, right? All those PMU, meters, and format of second category of data, both are different. Some type of data they generate images, right? And some type of data they generate some files, right? Whatever we will see later on. So if you just combine this, then this is just, I have given the overview, right? How much data that is generated. So if you consider these smart meters, let's say I am considering 0.5 million devices we have installed, right? So then they are going to generate 120 GB data per day. If you acquire, if this meter acquires, collect the data at a rate interval of 5 to 15 minutes, right? If it is higher, then again this will be different, right? This is just an overview. If I have synchrophasor devices, PMU, then 100 devices, 100 PMUs can collect data 2.5 GB per day, right? So they can collect 2.5 GB phasor data per day if you have, let's say, 240 samples per second. If you have other, let's say 120 or some other, then this value may be different, right? Same way, if I have GIS or GPS data, some additional layers are required to collect those data, because format of this and format of these two are entirely different. And let's say we have a accuracy of GIS and GPS data that is in terms of nanosecond. Usually it is. Weather data, again, let's say if you have radar system, it can generate over 50 GB data per day. And this we are collecting at an interval of 1 to 10 minutes, right? And seismic data, of course, 200 GB of raw images per day they generate with an interval, assuming that they are collected at point not 1 to 100 samples per second, right? So this is just an overview. Now you think every day, if I have more than 1500 PMUs, then how much data they are going to generate, right? If I have meters, of course, this is very small numbers in meters, right? In our country. So we have many more meters, right? In terms of millions or maybe billions. So then how much data they are going to generate, how we are going to handle those data. Okay, now regarding the just an overview that you have already, Professor Sidhu already told about the IEC 61850, right? And he just talked about the DNP3 also. So if we just compare, right, this DNP3, right, with different colors, let's say C37.118, that is for your PMU to PDC, and of course your 61850, then what are the comparison, how we can compare, right, these things. So if you just look at DNP3, then the major characteristic is that the slow rate is their slow rate, right? This DNP3, which is mainly used for SCADA systems, its data rate is very slow, right? Of the order of 0.1 to 0.2 hertz, maybe sometimes in minute also. So average latency you will get in the form of 100 millisecond to 2 seconds, right? That is there, always there. Inferior scalability, scalability is not proper, like you get here in 61850, as Professor Sidhu told. Then you have a limited support for very large payload if the volume of data that is very large. then DNP3 cannot handle those things, right? Then in that case, you need you have to fragment the data. That will again increase your latency and so on. And the data loss issues are also reported, right, in DNP3, right? And that is also because of when the volume of data that is very large. And the main point is this thing, last one. There is no end-to-end security, right? Cyber security aspect that is not covered in DNP3. Anybody can, any attacker can enter and just do the attack on this one, right? So that is also there. The second, let's say C37.118, which we are going to look at maybe after 10-15 minutes. So there the latency time you see that is 2 to 5 milliseconds, where the earlier case it was very high, right? Scalability challenge is still, this is also going to face the scalability issue when the large volume of data are there. And why large volume? I told you earlier slide, right? That how much data that is generated by each smart devices. So that is there. So that's why this large volume of data that plays an important role. And then this standard is not able to handle large and diversified data set. Large and diversified means the entire let's say their form of in which their data are collected, those are different, right? Images and like that. Again, cyber security issues are still there in this C37.118. This standard has not covered anything about cyber security issue, right? So you can have any type of attack on this. One can do those type of attacks also. And last one, which is already covered, right, by Professor Sidhu, that is 61850. This is usually effective for local area networks, right, within the substation. Usually 61850 is not used between two substations which are very far, usually, right? This is the normal practice which is followed by most of the developed countries. Of course, in our country, we do have, right? We are using this thing. Again, this also faces an issue with when the data volume of the data that is very large, right? And average latency you will get 3 to 4 milliseconds, similar to this one, right? C37.118. So both are comparable, but still you have the cyber security issues are still there. And as Professor Sidhu covered, other than this, again you have to go for 62335, right? For that you have to go in that case. Okay. Now regarding distribution side, right? If you consider the this what we talked about, all the earlier protocols, DNP3, C37.118, and the third one 61850. Those are used for at transmission level, usually EHV and UHV level. But if you just talk about the distribution side, then the scenario will be different, right? There you can see that of course the you can use wired or wireless communication, right? Those remain same, there is no issue. But here there is an issue, right? What you are going to cover here. So if you just look at, for example, right, maybe I'm not going to discuss all, very difficult, but just let's say IEEE 1850 field equipment, I have written here. This is a protocol oblique standards for utility side, and parallel to this, I have written here protocols and standard for consumers. So if utility is using, let's say, IEEE 1815, then consumer is going to use IEEE 2030.5, like that. If let's say utility is using IEC 61968, right? This is for demand side management or like that. Then consumer is going to use, let's say, OSIS or maybe some other similar compatible protocol, like that, right? So one-to-one matching is there. For example, if they are using Modbus, then you are going to use SCP, like that. So same way, for example, if we look at this two, right? Let's say IEEE 1815 and let's say IEEE 2030.5. So if you just look at this one, 1815 and 2030.5, 1815, it's a DNP3 based protocol again. So again, you assume that it has a it has an issue with data rate, slow data rate, and latency is very high, right? So this is mainly used for communication between inverter based resources. So whenever you have any DER, and when they want inverter of that DER wants to communicate with other control center or some other device, smart devices, then this protocol that is used, right? And this type of protocol is also used in water and power flow meters. Water flow, anyway, in our country, water is not chargeable, right? Except maybe, I think in one or two cities it is chargeable. I don't know. Otherwise, it is free of cost, right? But in developed countries, if you go, then like in Canada, this is chargeable, right? Water meter is there, and you cannot use water like we are using here in our country, right? You can use, but you have to pay the charges. And it is also used for communication among the distribution feeder devices, right? This is there. Now this is utility side. Now if you just look at on the consumer side, then they use IEEE 2030.5, right? So this protocol is also known as the SAP 2.0, right? So SAP means it is a smart energy profile, like that. So there are various versions of this SCP 1.0, SCP 2.0, like that. Now this on consumer side, these protocols are used either TCP/IP or HTTPS based on this, and it is going to establish the two-way communication between utility and various DERs. So like that, you can use utility can use this protocol. Then equivalently, consumer has to use the equivalent compatible protocol here also. So this is just an example, right? That if you have solar, battery energy storage system, EVs, or let's say smart meter, then they can send the data right to your energy management system, right? That is there. It is sometimes also known as CEMS, Central Energy Management System. So this is there. Same way, if you consider, let's say this example, right? This one, IEEE 61968. So then that also utility side, if you just look at, this is used for exchanging the information between the software application in DMS, right? So here in this case, data sharing that takes place among various DMS components, such as let's say for example, distribution network operation, asset management, customer support, like that. This is utility side. And the consumer side, you see the communication of this is related to the energy market, right? That what is, let's say for example, what is the price, what is the reliability, what is the emergency alerts, all those things, and all are based on this XML vocabularies. XML is nothing but your extended markup language, right? So they give you the vocabularies, and based on that, these different parameters they are going to monitor or observe. So like that. So same way here, distribution side, different this utility side, different protocols are there, and equivalently you have the protocols. Like for example, if you use 61850, whatever Professor Sidhu discussed, you can use at distribution level also. Then equivalently, consumer has to use the equivalent compatible protocol. For example, open, let's say advanced demand response type of protocol, they have to use it. So this is also the again the another protocol which is developed by the US. It is US based protocol. Same way for metering purpose also, utility can use this protocol, and the consumer side you can use this protocol. Okay, so I am not going to discuss now. This is important. Now, how to analyze this thing, right? Let's say we have some cyber attack, for example, right? Something happened. Now, how to analyze this? So there are two ways. The first is, for example, we analyze this type of attack or anything happened. So what we do is we just develop some prototype in lab, we test it, and then we deploy it in the real time. That is one of the way, right? How it is working in the other countries. So if I want to do that, right, then again I gave you the example of cyber physical system, which contains physical and the cyber system, two part. Now in physical system, for example, whenever you have any physical process, if you want to, let's say, develop some prototype in lab, then you need something, right? Let's say, for example, some software, some emulator, or some simulator, right? That is required, real time simulator. So you can use any of this, let's say RSCAD, which is RTDS, then PSCAD, DSpace, SpeedGoat, Simulink, LabVIEW, anything you can use it, right? And then as a sensor, collecting, let's say, the data. For example, let's say you want to collect data of IEDs, maybe you want to collect data from PMUs, you want to use GPS, CTPT, then you can use any of the, let's say, any of the devices, right? Manufactured by SEL, GE, ABB, Siemens, or anything, right? Usually in our country, we will go for the GE only, right? Because it is cheaper. Usually it comes L1, right? SEL never comes L1. Uh, am I right? Yeah. So this is ABB now. ABB is diversified now. ABB is not there. ABB is dealing only with motors. Motor part, motor division part is there. Now it is dealt with Hitachi. But Hitachi issue is that there is no after sales and support. It is very poor. At least I observed in our, let's say, in campus, Hitachi has donated something, right? Even in front lawn side where we have a group photo, on right hand side there is a big inverter and setup which is donated by Hitachi, right? They have installed. They have a very good ceremony, right? Inaugural photograph, everything. But then he is not working till now, right? So after sales support, that is very poor of Hitachi. Right? That is, even they install data center also. Whatever they have installed here, all the data that will go in some center where they have given some, donated some RTUs and so many things. But now they are not working. Right? One card is not working, and they said uh, we are sending, and I think it has passed more than 2 years. Still, we are waiting for the cards. So that's why GE usually is there, but SEL is a good product, right? If there is no issue of cost, then you can go for SEL. Okay. Now, regarding the other side, right? Cyber side. So here, when the real-time exchanges that will take place, communication side, you can use several things, right? Several ways, like NetSIM. We have already, he has given the right the demo. What is the capability of NetSIM and all? You can use OM Net Plus or NS3. Many things you can use. And then at control center, where you develop your algorithm, write your algorithm, you can use MATLAB, Simulink, RTEC, Python, C++, or FPGA boards, or any controller, DSP based or anything, right? So there you can develop your algorithm, and then again you can, through some medium, you can pass it to actuators, and you can control your physical process. So this is what usually we need to do in laboratory. Once this is done, then you can deploy it in actual field, right? That is there. So now if I want to do this thing, right, all the process, two process in physical part and two processes in the cyber system part, then I need few things, right? Few important points I need to remember. The one is the synchronization, right? That means there is a continuous, you have to maintain the coherence between the continuous and discrete simulators. This is there, right? Of course, synchronization is also required when your PMU deals with PDC, right? But PMU usually uses GPS clock, so there won't be such type of issues. Scalability is also there because you have to handle large volume of data, so that is there, right? Uh, you have some constraints are also there. Mainly the latency related issues are there that you need to handle, right? When you have earlier slide type of setup in lab, and maybe when you deploy in the real time also. And then you have the interoperability issue, because anyone you have, let's say I'm not utilizing SEL based product, I'm utilizing G based, then my system should be such that it is capable to adapt all, right? So this type of interoperability, that is also there. Because earlier you remember when we started the use of MATLAB, roughly around 1990s, right? I don't know. Well, I started learning MATLAB in 1990s, 92 or like that. At that time, we used to run the MATLAB using, I think, 10 or 12 floppy disk, right? And if one is corrupted, then everything is gone. So there, right? At that time, MATLAB is not compatible with other softwares or like. But now MATLAB, it is compatible with OpenRT or now RTDS. RTDS has latest version Nova Core, so it is compatible with all, right? So that is there. And then finally, it comes the validation and verification. So that is slightly commercial issues are involved before you deploy into the real field. You need to go for several processes, prototyping and standardization and all those things. Okay. Now, before we just discuss the what is the IEEE C37.118, how it looks. This is just the, I want to give you in 5 minutes, what is the overview of PMU, what is that. So this is the diagram of generic PMU, right? How PMU looks like. So it is nothing but it is similar to ID, right? In ID also or relay also, you remember, you have some, let's say data you are going to acquire using CTPT or CT or CVT now, right? Then you have isolation circuit and signal conditioning circuit where you want proper isolation, surge protection, and then you do the all the signaling part, right? Let's say sample and hold and conversion from analog signal to digital signals, and then you give it to some processor, any kind of processor, right? And this processor is connected with some communication device. And of course, this processor is also connected with local, let's say some oscillator block is there. It is there in PMU, right? Because you want to, let's say, adjust the clock of PMU, right? Time stamping is required, then time stamping is done using this, right? Of course, some other process need to be followed, right? And then you have a receiver of GPS, that is you have to install, and which gives you the second of century pulse, right? We will see later on what is the file structure of PMU. Now, if you just look at what is the hierarchy of PMU, where PMU need to send the data. So lower side, I have shown all the PMUs, right, with some storage capability. But PMU has very limited storage capability, right? PMU cannot store the data. What is the storage capability? Utility can tell, I think, better. Not more than, I think, 1 day, right? Every day they are going to overwrite the data. So what they are doing, right? In the substation where they are is they have installed the PMU, because I visited one here PMU station in near Delhi, uh, NLDC. There, what they are doing some, let's say, important flag they are marking on PMUs. Let's say these are the events which are very important, and for those events we need data. So then they flag it. So whenever the overwriting of data takes place next day, then those data that is not overwritten, that remains as separately, right? So that is what they are doing. Now all the PMUs, see, the hierarchy of PMU is this hard line. The data always flows from downward to upward, right? This is dotted line is very rare, right? It is there only when there is something goes wrong on upper side, right? Otherwise, it is similar to your boss, right? Boss will never come to your office. You have to go to his office. It is similar to that. So all the PMU, they are going to send the data to PDC, phasor data concentrator. And if, let's say, your number of PMUs are, let's say, more than, let's say, 100, 200, 500, then you have one PDC is not sufficient. So then you have multiple PDC, and then you have super PDC also. That is also there. So this is the normal hierarchy of how the PMU is going to send the data. Now, if you just look at, this is not required. Yeah. Okay. Now, what is the function of PDC? What the phasor data concentrator? What is his function, right? Which is very important. So all the data, right? Let's say, for example, usually it is usual practice that 8 to 10 PMUs are allocated to one PDC. So that PDC is going to collect all 8 to 10 PMUs data, right, at regular interval. So the function of the PDC is that it is going to assemble all the data, obviously assigned under that PDC from PMUs. It rejects bad data. So bad data rejection is already done, right? That algorithm is already there. I hope you have learned in undergrad or I think MTech level, bad data detection and rejection. So those algorithms already there inbuilt. It aligns time stamping is also done by PDC, right? So PMU never does timestamping. Timestamping is always done by PDC. And then it is also going to maintain the records of all the data, so that if something goes wrong, if any postmortem analysis is required, then that can be done. Of course, it has some storage facility and all. I think that is not okay. Now, when the down, as I told you, upward flow is always there, right? Hierarchical. When the downward flow is possible, right? Reverse direction. So this is possible only in certain critical conditions. For example, some commands are required or issued by PDC to specific PMU, right? That you are not performing wrong or this is wrong, like that. And if your PDC wants to have access the data in particular form, right, then the downward or reverse direction, that is possible. Otherwise, it is always upward. Now, whenever PMU, let's say, sends the data in the form of packets using this C37.118 to PDC, then two things are very important, right? One is what is the capacity of the channel, right? What medium you are using. Usually, it is measured in kilobytes or megabytes per second, right? Usually. And second is the latency. Latency you can define as it is defined as the time lag between the time at which data is generated or created and the time at which it is available, right, for desired application. So when PMU creates the data and when it is available to PDC, that difference is nothing but the latency time, right? So these two are very important points. And of course, I think most of the utility, they use fiber optic links because of these three main advantages. I'm not going to discuss this thing, assuming that this is very known. Its capacity is good, high data transfer rate, and this fiber optics is immune against any type of interferences like electromagnetic or maybe radio also. This is how the fiber optic cables are, let's say, installed. Maybe you can install the fiber bundle in ground wire, that you can do. This is your transmission tower. You can also, let's say, install here also, right, a fire bundle separately, and the other way you can install at the ground level. So there are various ways, right? I don't know which method that is used in by utility in India. I don't know. You can tell me, right? This first one, I think, right? This is the common one. Yeah. Okay. Now, C37, right? How it works. So when we consider the any PMU, right, which is going to send the data in the form of packets to PDC, then you have to consider the protocol, specific protocol. They are also doing encryption. It is by default. So whenever PMU sends data, they never send data like as it is, right? They encrypt it and they send it. So by default, this encryption and decryption is already there between PMU and PDC. So PMU sends the packet in encrypted form, and then whenever it is available to PDC, PDC has to decrypt it. But anyone can decrypt it, right? It's a very small algorithm. Anyone can write it. And uh, the other thing which is very important, ordering of the data. It is always not like that PMU is going to send the data first is, let's say, first is time stamping, then you have voltage, current. It is not like that. Ordering can be changed, right? So it is up to the PDC that how in which form PDC wants those data. uh, the easiest way to communicate, earlier when we installed the PMU, the communication was done using RS-232. Now it is not used, right? Uh, of course, it is up to us that whether we will go for TCP or we will go for UDP, right? It depends. Uh, of course, you can use the internet protocol also, right, for some of the functions. That is also there. Okay. Now, yeah, just standardization part. What we learned till now, that we are using C37.118, which was given in 2005, right? Which was given in 2005, where PMU can send the data to PDC. But later on, it was amended in 2011, same C37.118.1. And later on in 2018, this was not there. Now what is existing is 60255, right? So now IEEE C37.118 is not there. Now you can have the protocol which is like this, right? This one. And this is same, right? The maybe this is more much more higher functionality than earlier two ones, right? As let's say Professor Sidhu told that 62335 is much more, let's say, higher capabilities than uh, uh, your earlier version, right? IEC 61850. Same way for this also, this is much more powerful, have many, let's say, dot one, dot two, many things are there, different capabilities it is going to cover. Now, what is the file structure of this PMU? How the PMU is going to send the data? What is in what form, right? So this is very important, right? So the file structure of all synchrophaser devices, PMU or PDC, that is based on this file, COMTRAD file, right? This is sure. So this is the file for transient data collection and dissemination, which is very commonly used. It is used by even fault recorders also, right? So this is the file format, and if you just look at this format also, there is also a history, right? Earlier, this C37 was initially it was given by 1991. Then later on in 99 it was amended, and then again in 2013 it was amended, and this file format is now adopted by 60255, right? Latest version. Okay, now what are the files, right? Whenever PMU sends the data, how many files are there? So usually it contains four types of files. One is the header files, another is the configuration files, third is the data files, and fourth is the command file, right? So if we just look at the first one, header file, then this file is readable by humans, right? We can easily read it. It is not encrypted. This file is basically used to share any kind of data which is produced with the customer, right? That okay, this is the data we have produced during, let's say, a commissioning or testing part. This we are giving it to you. So whatever the user or customer who purchase PMU, they can read this file, right? They can have the access of this. The second file is configuration file. So configuration file, it is a machine readable file with specific format. Which format? Again SCL. As Professor Sidhu told yesterday in IEC 61850, right? So that is there. So same format. So this gives information related to the interpretation of data contained in the files. What is the data? What is the time stamping? What is the first row, second row, third row, right? All those things. Whether you are having voltage values, VA, VB, VC, whether you have sequence components also, V0, V1, V2, you have current phasors, IA, IB, IC, or I0, I1, I2, or frequency or rate of change of frequency, right? So all those data, that is information that is available in this file. Then you have the third data file, right? So this is also machine readable with again same format SCL, and this contains the let's say output of PMU. Right? You know what is the PMU? It's a device where you give continuous value, acquire the data, right, from ADC or some other sensors. You give it, and then output of PMU, that is nothing but what is there? That is your phasor value, right? So I hope all are aware of that, how the PMU is going to calculate the phasor value, right? So I am not going in that detail. I hope you are all aware. What they do is that, let's say you have the, for example, three currents, IA, IB, IC, right? These currents are instantaneous currents. You acquire from, let's say, your sensors or ADC will acquire it, and then you convert it in digital form, right? And then you give it to the PMU input, and PMU do some algorithm is there, right, inside the PMU, and the output side what they give, let's say, IA angle phi A, IB angle phi B, IC angle phi C. So magnitude and angle part, that is nothing but your phasor value, right? Polar form or rectangular form, maybe whatever form you desire. So inside this PMU, they do the phasor estimation. They run the phasor estimation algorithm, and you know, you are well aware of phasor estimation algorithm. you can use the discrete Fourier transform, you can use cosine transform, you can use let's say LES, least error square technique, or you can use Kalman filtering, or maybe anything else, right? So these are the main four techniques which are used for phasor estimation. Each has certain advantages and the disadvantages, right? So this is what they are using, right? And whenever you use any of the technique, each technique has its own advantages and disadvantages. Actually, in PMU, they use the recursive DFT, right? So that the memory allocation, you can have save the memory and computation time. So that is what they are using inside the PMU. And fourth one is the command file that is contained by the PMU, and this is the file which is used by the PDC. So when PMU communicates with PDC, it is this communication is done to the command file. So if you just look at what is the file structure of PMU, then this is the file structure of PMU, right? Where you can see that the first this thing contains the synchronization command, and this is of the, I think, 2 bytes, right, in size. And the after that you have the frame size and the ID code. So frame size that contains the total length of the data, right? Whether you want currents, voltage, frequency, rate of change of frequency, depending upon that, this changes. And then you have ID code. So physical ID code is there, IP address, you can say, that is there. And then here in, sorry, this is fifth, fourth and fifth, you have the SOC and the other two fraction of second. So this is the SOC and fraction of second. These two files are there. It is second of century and fraction of second. That is also the data given. Here you have the actual data, right, which is there. PMU wants to send it. And then there is another file known as checksum. So now what is checksum? So checksum is that, let's say for example, your PMU has calculated the phasor value of currents, for example, right? Three currents, IA, IB, IC, magnitude and angle, that is calculated by PMUs. Now, whenever this checksum is a specific type of format, whenever now how this PMU is going to calculate your magnitude and angle of three currents, so they take some data, right? Obviously, one cycle data is required. Uh, Instantaneous values of currents are required, all the three currents for one cycle, right? Let's say. So one cycle, 20 millisecond, even I think 2 or n plus 2, where n is the number of samples in a cycle. So that much data is required for calculation of the phasor value. So whenever now anybody can, let's say when you acquire this one cycle data, right, it's a continuous data, instantaneous values, anybody can temper those data. So if you have temper those data, then this checksum is going to have the summation of those data. And if the summation is within certain limit, then and then this is going, whatever data that is to be there, that is the correct one, correct data. Otherwise, if that is not within the limit, then they understand, this device will understand that, okay, this is not, someone has done something, and this is not the correct way, right? So this is by default, it is there inside the PMU, right? It is already there. Okay, so I think I stop here, and I will continue tomorrow. Maybe further, what is the setup we have in this lab, right? And other attacks which we have done. So that I will continue tomorrow. Any questions